Okay, and the first ones are a little bit easy. Don't think like I made them this way just to make you guys feel good about, what's it called? You know, feel good about your knowledge. It's just fundamental stuff. Make sure everybody gets there. So, yes, final exam review. Number one, the charge on a proton is the same as the charge on a neutron. No, right? Charges of neutrons are neutral. They have no charge. Same as the charge on an electron. Yeah? You guys agree? Not quite, right? Equal but opposite in magnitude, okay? So, well, equal in magnitude but opposite in charge, okay? So we'll have the charge on the electron but opposite in sign, okay? So who can tell me what that charge is? Who has it memorized? Awesome. The exponential is the most important part, right? Times 10 to the negative 19, but we'll see it's 1.602 times 10 to the negative 19. Those are really good just conceptually to keep in your mind. Like you don't have to, what's it called, memorize them completely, but the magnitude of the exponential is pretty important for understanding concepts. But yes, moving on. When a glass rod is rubbed with a piece of silk, the glass rod acquires a positive charge and the silk acquires a negative charge. This process signifies that A, the glass rod was not rubbed very hard with the silk. B, the glass rod lost electrons to the piece of silk. C, the glass rod was rubbed very vigorously with the silk. Or D, the glass rod gained electrons from the piece of silk. Okay, so if the glass rod acquired positive charge, it gained electrons, or did the silk gain electrons? The rod or the silk? The silk, right? So we'll have, it was that the glass rod lost electrons to the piece of silk, okay, because the rod acquired positive charge. And this is just kind of, hey guys, sorry to miss you guys. You probably thought it was in that room right there. My B-dog, okay. Good to see you guys here. I have some, yeah, come through. Welcome, all of you guys. I have some, yeah. Yeah, I thought you guys were at the tailgate. I was like, what the heck? Where's my crew? So here's some sheets. These are just evaluations here. I'm gonna pass those around. You can fit in over here. You can go. If you want, you can put your skateboard. Shake my hand first.
All right, I'm sorry.
Here we go. Everybody else needs some sheets. Here we go. Just take one, pass it down. I'll say, do you have one? Can you pass one down to him, please? Cool. Yes, here. Here you go, just an eval. You're the only one. I'm going to put these over here just in case more people come. But just to recap, you guys, we have my worksheet that we're going over. You know, I'm sure you guys know it's mostly concepts in this first one. I formatted it as a multiple choice. You can find it on the UCF studyunion.wordpress.com website. Okay, just go to like the physics tab, and then from there, like, you know, you can scroll down. It's like the third to the last one on the bottom. And you can have it for yourself. You know, if you don't have a computer or anything, you can just copy down the answers and kind of like the processes that I'll do, because I'll do my math here. I have like some extra sheets of paper that I'll be working on. Excuse me. I have some piece of paper that I'll work on for any math I do have, because it's not like completely mathless, you know. But yeah. So yes, two charges with Q1 and Q2 are separated by a certain distance r. If the magnitudes of their charges are doubled and their separation is halved, then what happens to the electrical force between these two charges? Well, we see that it increases by a factor of 16. Yes. Yes, thank you. Okay. You may have to constantly remind me, okay, even though it's like should just be in my periphery, but like I'm kind of focusing on you guys. But yes, will it increase by a factor of 16? Will it be quadrupled? Will it be doubled? Or will it stay the same? You know, honestly, immediately looking at this, I wouldn't know like right off the bat. We'd have to take out our Coulomb's law, okay, because we're looking at electrical force, write it out, you know, put in some fake numbers, you know, simple but applicable numbers and see what happens. So we have our Coulomb's law, which is what? Who can tell me? Nobody can tell me.
KQ over R squared.
KQ with the extra Q, awesome. So KQ over R squared, but times another Q, right? Because we have a force in between two charges. So we're going to see force is equal to K times Q1 times Q2 over R squared, right? So let's say Q1 is equal to 1, Q2 is equal to 1 as well, and then the radial distance is equal to, let's say, 2, you know. If we plug this in, we have K times 1 over R squared, which will be 4, right? So then we're going to take that and see that it's simply K over 4. But if we double those, right, well, if the magnitudes of the charge are doubled and their separation is halved, okay, so then this is 2, this is 2, and then this is halved, so then we have 1, so essentially it switches. We'll have now our Coulomb's law is going to show we'll have K times 2 over 1, okay, and then that'll come out to 4. So we went from 1 over 4 to 4. Okay, and if we do that math, it's going to see that it increases by a factor of 16. And if you don't want to plug in like dummy variables, okay, so instead of dummy variables, you can just take this right here and see that, you know, just kind of utilizing the space up here. K 2Q1 times 2Q2 over 1/2 R squared will kind of simplify to K, well, 4K Q1, Q2 over 1 over 4th, because the 1/2 is squared, R squared, and then we bring that 4 up, so then we get essentially force is equal to 16 of the, like our force final is equal to 16 times the original force. I apologize, it's a little blurry. Let me see if I can wipe this up. Yeah, it has nothing to do with the fog, it's just the cam. But nonetheless, any questions on that? Not too hard, right? Not too hard. So let's see, the force of attraction between a negative 40 microcoulomb and a positive 108 microcoulomb charge is 4 newtons. And I put a little U because I didn't know how to do micro on Microsoft Word. But yeah, what is the separation between these two charges? Okay, so again, we see a force, so we're going to go straight to our Coulomb's law, which we discussed earlier. Okay, let me get out my red pen too, get some multicolor up in here. So we'll see our, wow, it looks the same, but it's red. Looking at it, so we'll take our equation, we'll see that force is given to us, which is 4 newtons. Okay, so actually let's write 4 newtons is equal to the first charge, well, K times the first charge, negative 40 times 108, and these are micro, so we'll do times 10 to the negative 6 twice over R squared. Okay, so we're going to solve for R by timesing over the R, dividing over the 4 newtons, rooting all of it. Okay, and if we work this out, okay, we should get 3.12 meters. Okay, I'm not going to, you know, waste your time plugging it in. I have an answer key right here, but please do so. Like, follow along. You know, if you have calculators, bring them out. Kind of do the math, because it might be wrong. You know, if it is wrong, like, let me know.
How do you get the R squared again outside?
The r squared outside, I just multiplied on both sides. So, you know, coming up here just to show my math, I had force is equal to K Q1 Q2 over r squared. I timesed over the r squared, so then I had F times r squared equals KQ, yeah, and then divided by the force and square rooted to cancel, okay? And then that was my final equation, okay? So let's see, 2-point charges of 60 microcoulombs and negative 12 microcoulombs are separated by a distance of 20 centimeters. A positive 7 microcoulomb charge is placed midway between these two charges. What is the electric force acting on this charge because of the other two charges? Okay, awesome. A point I want to make before we move on real quick is last time I didn't really take into account the direction of the vectors, because essentially we had two charges, right? You know, one was positive and one was negative. So if they're opposite in charge, they'll attract. You know, if we look at them, the left one will feel a force to the right and the right charge will feel a force to the left, okay, because they're going towards each other. But here, you know, like it didn't really ask for direction or anything like that. But here, direction is going to be important for us. Why is direction going to be important for us for this problem? We have, you know, electric field from multiple charges acting on one single charge. Do you have anything you wanted to add?
Yeah, I was just saying, like in the answer, we have to specify whether the force is going to be in the positive or negative.
Awesome. So you could see in the answer choices what direction it's going to be in. Is there anything else you guys want to add? Massimo? You're given a position for a certain particle. Awesome. So if like we had the third particle outside, you know, it might feel a force to the right as opposed to the left. Also, we will want to know if we are adding or subtracting the forces from each of the charges. So in this example, the third charge is placed midway between the two charges. So we're going to look right here. So here's Q1, here's Q2, and here's Q3. Okay, Q1 we see is positive 60 microcoulombs. We see Q2 is negative 12 microcoulombs. And then the third one is positive 7 microcoulombs. Okay, so we see here one force, these two are positive, is going to push it away, but these, since they're opposite charges, will attract. With that, we see that the vectors are in the same direction, so we will add them. If this were positive, then the vectors would point in the opposite direction, and we would have to subtract them. Does that make sense to everybody? So let's plug it out. So we'll define this top vector, the force of 1 on 3, and then the second force as 2 on 3, the charge 2 on the third one, okay? You know, this is just kind of a little notation that I use. Sometimes you can use a comma so it doesn't look like force 13. You know, if you get into big, you know, like a lot of charges out in your space, you definitely want to put a comma there if you have like 11 charges or whatever. But if not, I usually disregard that comma. Our total force is going to equal, so F total is going to equal the force of 1 on 3 plus the force 2 on 3. Okay, and let me just put my little vector symbols. Since they're pointing, you know, in the same axes, we could simply add them together, right? But if, you know, our third charge was placed like not directly in between them, but kind of above them or below them, we'd have to do some vector breakdowns, right? We'd have to use our trigonometry to break up, get our axes, and then simplify it, okay? You guys want to make sure you're capable of doing that. And I think I have a problem later that will exemplify this. Thus, our force total will simply be force 1 on 3, which is going to be K Q1 times Q3 over R squared. And what's going to be our R, okay, given by this problem? 10 centimeters, okay? And we want SI units, so it's going to be 0.1 meters. So we'll see it's 0.1 squared plus KQ2 times Q3 over 0.1 squared again, okay? Yes. Yes, of course. Thank you. So we'll see that this is like that. And, you know, just to simplify, if you have to plug it in your calculations, it's a test, you're timed. You want to like be, you know, be cautious of your times. You can factor out all of the similar variables, right? I'm sorry, Q3, and then this would be Q1 plus Q2. Okay, so just moving this to the focused side. We have KQ3 over 0.1 squared, which is just our R, times Q1 plus Q2. Okay?
In the formula are the charges, the absolute value, so if there's a negative.
Awesome. Yes, so let's take a look at our Coulomb's law. We'll actually have the absolute value of these because the positive and negative doesn't essentially change the value of the force. It just determines direction, okay? But what I did here was I just drew out my direction. I took into account the fact that they're positive or negative, pointed out the direction, and then conducted my math. Thus, we use the absolute value of, okay? The negatives are just to determine direction. Anything else? Very good question. Thank you. Or statement. No? Cool. Okay. So if we do this, we should see a 435 newtons directed towards the negative charge. Okay, so we see here the negative charge. Both of ours are there. You know, immediately we can cross out towards the positive charges in our answer choice. And anyways, you could probably even come to the conclusion without even doing any math by just looking at our magnitude. So we have microcoulombs times 10 to the negative 8 over here. So 2 microcoulombs will come together times 10 to the negative 12 times 10 to the positive 9. Those will cancel out. So then we have, what is that? 12, 9 minus 12 would be to the negative 3, but divided by 0.1 squared, which is 0.01. So divided times 10 to the negative 2, we get, you know, like to this magnitude, okay? But you could, simple calculations. Here we have the units of electrical flux are what? Okay, I'm not even going to give you guys this one. Who could tell me right off the back?
The what?
The units of electrical flux. What? B? Does everyone agree? A? Why?
Because flux would be electric field times the area.
Okay, it's electric field times the area, and electric field is what?
Newtons per newtons per.
And then area, of course, is meters squared. Okay, and then we'll see that we get Newton meters squared over Coulomb. Or what's another way we see electric field? Voltmeter. Awesome. So we see voltmeter times meter squared will simplify to volt. Voltmeter. So volt per meter times meter squared equals voltmeter. Okay, so don't forget the per in your dividing units. Okay. Awesome. Awesome, awesome, awesome. Moving on. We have a charged particle traveling along the positive x-axis and enters an electric field directed vertically upward along the positive y-axis. If the charged particle experiences a force downward because of the field, what is the sign on the charge of this particle? Positive? Negative? Anybody else? One for positive, one for negative. Who says positive? Who says negative? You say it's negative? Never mind. So we got 2 for positive, 1 for negative, and there's, what, 30 of us in here? So I'm going to read this again. Let's see if I can get some more votes. Okay, think about it. We have a charged particle traveling along the positive x-axis. Okay, so let me face so towards the positive x-axis. It enters electric field directed vertically upward along the positive x-axis. If the charged particle faces an experience downward because of this field, what is the sign of this particle? Negative, right? Because we have positive charges flow with electric field, negative charges flow against electric field. Okay, so we're going to see it as negative. An electron is initially at rest. It is accelerated through a potential difference of 400 volts. What is the kinetic energy of this electron? Okay, so what are we going to do here? We look at what we know. We know it's 400 volts. We want kinetic energy. Okay, so kinetic energy is equal to what? 1/2 mv squared. Awesome. What are some things we know? We know the conservation of mechanical energy, right? So we'll have so kinetic energy initial plus potential energy initial is equal to kinetic energy final plus potential energy final. Okay? So if it starts at rest, what does that mean? A little bit louder? Initial kinetic energy is 0. Okay? And if it goes throughout the entire potential difference, then we'll see that our potential energy final is 0 as well. Thus, our potential energy equals our kinetic energy final. Thus, what equation do we have for the potential energy of a particle?
Q times V.
Q times V, awesome. So we'll see it's just Q times V. And if it goes throughout the entire thing, we can actually say that our kinetic energy is delta V times Q if it goes throughout it, thinking conceptually here. But yeah, so we take the charge. Our electron is 1.6 times 10 to the negative 19, as we discussed earlier, coulombs. And we multiply this by a change in potential of 400 volts. We'll see that we get our answer to be 6.4 times 10 to the negative 17 joules. 6.4 times 10 to the negative 17 joules, okay? And honestly, this question is kind of stupid because you can look at the answer choices here. Negative 19 times 400. We don't even need to do any math. You know it's none of these, right? But yeah, nonetheless, this will help you. This will help you guys out. Don't think this is like too easy or nothing. Okay, without the fundamentals, you can't hit the good stuff. Okay, that's why you guys should also come to my Monday session, right? Who's gonna be there? Show of hands. Hey, turn up. Okay, 4 to 6, right? Yeah, 4 to 6 p.m. Same spot. It might be in that room. I don't know. They just say Key West Ballroom. Apparently, there's 2 Key West ballrooms. But yeah. The electron volt is a unit of electric field, charge, energy, or potential. Come on, who can scream this out? Potential? Awesome. Anybody else? Potential? Anybody else? Wrong. You got it's potential It's energy, right? Because we'll have, right, the electron volt. Let's look at our last problem. The electron volt gives us energy, okay? And, you know, the electron volt, 1 electron volt is equal to 1.6 times 10 to the negative 19 joules, okay? That's super important, especially if you're going into physics 3, or if you're doing, you know, like you go into the workforce. A lot of our calculations are done in the electron volt just because it's more real, okay? Like we're not going to be dealing with magnitudes to negative, you know, 17, negative whatever, okay? So this is an important number to know, the electron volt to the joule, okay? Yes?
I thought voltage was like a measure of potential energy.
It is voltage, okay, our electric potential, but our electron volt is our electric potential times Coulomb, times our electric charge.
Okay.
You see that question? But yeah, so it's electric potential multiplied by charge. So it's not just electric potential exclusively. Good question though, thank you.
If anybody cares, UCF1.
Hey, you hear that? UCF1. Go Knights! Score? 56-41. Yeah, Josh keeping count. He was tailgating earlier. I saw you. Don't worry, I was there too. Ooh, okay. Let's see, what is it? Don't mean you can't do math, okay? Just because you have fun don't mean you can't do math. An 800 voltmeter electric field is directed along the positive x-axis if the potential at x equals 0 meters is 2,000 volts. What is the potential at x equals 2 meters? All right, what are we going to do here? How are we going to set this up?
Wait, by direct along, you mean like going towards the positive x-axis?
Mm-hmm. Along the positive x-axis. So if we were to draw this out, I need more paper. There's not enough room to get one of these sheets here. Okay. So let's kind of draw this out a little bit. So we have 800 voltmeter electric field, like someone mentioned earlier, another unit that we have, okay, is directed along the positive x-axis if we use standard configuration. Here's our electric field. Okay, if the potential at x equals 0, here's x equals 0, is 2,000 volts, so volts equals 2,000. What is the potential at x equals 2 meters? So let's say we come here, x equals 2 meters. What are we going to do? Does potential increase or decrease as we go along the electric field? Decreases? Awesome. So we'll see that our potential at this position will be some number smaller than 2,000 volts. How do we like mathematically calculate this out? What equations do we know?
Delta V equals integral, negative integral E dot.
Awesome. So delta V equals the negative integral, not closed integral. Negative integral of what? E dot dl. Awesome. So we have a constant electric field, okay? So we can pull this out. The integral of dl is just L. Okay, and then the length is simply this right here, okay, which is 2 meters. We'll have the magnitude of our electric field, which is 800 volts per meter, times the length, which is 2 meters. We see our meters cancel, okay? And then we get 800 times 2. So then it's negative 1,600. So then this is just our change in potential, but if we start here, so our change in potential is equal to our potential final minus potential initial, right? We know our initial potential is 2000. We see that negative 1600 equals potential final minus, what was it, 2000. Thus, looking at this, we know our potential final is equal to 400. Okay, awesome. Thank you, Hunter. Questions? So we'll see here, 400. And according to my answer key, that is correct. Number 11. If more electric field lines leave a Gaussian surface than enter it, what can you conclude about the net charge enclosed by that surface? Okay? Positive? Awesome. It's going to be positive, right? If we have more electric field coming out than electric field coming in, it's going to be positive. The net charge will be positive. Okay? Why do we like Gaussian surfaces and Gauss's law and stuff? What is our application for that usually?
Finding electric fields at certain points.
We can find electric fields at certain points, and we can find how much charge. So if we just, making it, for his suggestion, if we want to find the enclosed charge, we just make a random Gaussian surface, and then we see what the electric field is around it. We can see how much charge is inside. Or if we don't know what the electric field is, but we know what the charge inside is, we create a Gaussian surface in which our electric field is constant at that surface. So then when we set up our Gaussian integral, we can pull out the electric field there, okay? And we have a simple integral. And then essentially we can calculate what our electric field would be, okay? So, yeah. Anything else you guys want to add to that? Yes. Yes, I can. So to find the electric field at certain points, what we do is we'd set up a Gaussian surface such that at the surface, our electric field is constant. So if we had a point charge, we'd set up a Gaussian surface that is a sphere. If we had a line of charge, we'd set up a Gaussian surface that's a cylinder. If we had a plane, how would we set up our Gaussian surface? Huh? Sphere, cylinder, box. Yeah, a cube, okay? We want a cube so that the flux would go through. A cylinder would work too, because as long as you have like one flat surface for the charge to go through and stuff like that, you just calculate you calculate the charge that's within your Gaussian surface. Because if you have a plane, you might not want to put all of it inside of your Gaussian surface, because a lot of the times they give you like an infinite plane to do your math on, and it's just annoying having to make an infinitely large Gaussian surface. So you just fit what's inside. You'd have to use some ratio to limit the plane to the charge, and you'd base that ratio off the charge density of the plane, right? And that's denoted by not rho, but sigma, right? Okay. A little bit of a parentheses, right? But yeah, so at a certain point in space, there's a potential of 400 volts. What is the potential energy of a positive 2 microcoulomb charge at that point in space? Okay. So let's see, at a certain point in space, there's a potential of 400 volts. Okay. What is the potential energy of a 2 microcoulomb charge at that point in space? We already did this, right? Potential energy is equal to Q times V. We have 2 microcoulombs, we times it by V, and we should get some number. Let's see, what is this, number 12? 8 times 10 to the negative 4 joules. Oh, yeah. Here we go. Any questions? Oh, it's just cake. Let's fly by that one. A 4 microcoulomb charge is situated at the origin of an xy coordinate system. What is the potential difference between a point x equals 4 meters and y equals negative 4 meters because of this charge? Okay. So let's see. A 4 microcoulomb charge is situated at the origin. Let's draw this out. So we have Q equals 4 microcoulombs. What is the potential difference between a point x equals 4? So here's x equals 4 meters and x equals negative 4 meters. JK, y equals negative 4 meters. But yes, y equals negative 4 meters because of this charge. So, yeah, what is going to be the potential difference? 0, right? Because it is not, it's a scalar quantity. It doesn't matter like what direction it is in space, like a vector quantity would. Potential is a scalar quantity. So as long as it's the same distance away, you know, radially outward from that charge, we'll see a constant potential, okay? If that's, looking at this, actually just kind of completing the circle, the potential, you know, we'll have an equipotential line like so, and then we'll have another one, and another one, and another one, and all of these will have the same. So, you know, this one will be equal to, the potential at this one will be K times Q over R squared, R being that, and then we increase it, you know, but we have a new R, right? So this will be R2, you know, over R2, and then this will be over R3. Thus, as we go outward, our R gets bigger and our potential gets smaller, okay? If it was a negative charge, you know, like we have negative Q, thus it'll get bigger, right? Because we have like negative 500 here, negative 400, negative 200, you know, it's getting bigger. But like, yeah. Any questions on that?
So if you had it x negative 4 would be the same thing?
X equals negative 4 would be the same thing. If we had two charges, right? So let's say a positive, like two positive charges, like our equipotential lines will be, you know, kind of like so. And I don't know if you've seen like, of course you guys have seen a map with mountains and stuff and valleys, and it denotes the height by like lines, okay? It's the same thing. You could look at a equipotential map and it'll look just like you're trying to hike through the Andes Mountains or something. You know what I mean? Okay. The only thing is our valleys are like accumulations of negative charges, and our peaks are accumulations of positive charges. Okay, and the reason, like, you know, how I like to conceptually think of this is positive charges, if they were on top of the mountain, they would fall off of it, right? You know, just like if I was on top of a mountain and I like walked like off the edge or whatever, I'd fall. Okay, and electric charges are opposite though. Like they want to go to the top. You know, they're like helium balloons. If you hold an electric charge at the bottom of a valley, okay, they'll float up it. They'll go away. Okay. But yeah, any questions on that? No? Cool. Okay, so let's see. A 4 microcoulomb charge is situated at the origin of an xy coordinate system. What is the potential difference between a point x equals 4? Oh, sorry. But just to give you guys a value, you know, 0, right? Which of the following will increase the capacitance between the plates of a parallel plate capacitor? Increase the potential between the plates, introduce a dielectric material between the plates, decrease the potential between the plates, or increase the charge on the plates. What do you guys think? We want to increase the capacitance, right? What's an equation for a capacitance? Hello.
A epsilon naught over D.
So capacitance equals A epsilon naught for parallel plate capacitor. That's fine to use for now.
I was going to say Q over delta V, or Q over the potential.
Or Q over delta V. Okay, this one is similar to using, like, you got to be careful. This is correct, but this is similar to looking at a resistor like V equals, not I over R, but V equals IR, right? Here, if we were to increase the potential, the charge would decrease proportionally so that our capacitance stays constant. Whenever you change either of these, the other will change proportionally, okay? Capacitance, based off of, you know, like if our circuit was off, right? A capacitor would be given some capacitance. You know, we're at Ace Hardware and we're trying to buy a capacitor for like our new toy we're making or whatever. And we see like the capacitances and stuff, they're completely based off of geometric quantities, okay? Have you heard of that before, geometric quantities? We, like this, we can see, you know, if we convert this V equals IR, we can use it to see the resistance is V over I, but you know, if we change the potential, the current is going to change as well, right? But our geometric quantity for resistance is rho times L over A, right? Which rho is our resistivity. This is what we will see at Ace Hardware when we're buying our resistor, right? Okay, the resistance will be determined by the geometric quantities. Okay, so this one we can't really, question? No? Stretching? Cool. This one we can't really use because it'll change if we change the other. Okay? Thus, if we're looking to increase the capacitance, we'll look to increase the geometric quantities, but we don't see anything here with area or distance between the plates. Okay, we could kind of go off intuition and, you know, crossing off, you know, increasing the charge, increasing the potential, or decreasing the potential. But what's it called? We can see here actually, you know, if this was a fill-in-the-blank problem, our epsilon naught is essentially E times, you know, the dielectric. Who knows what the kappa, right? So we'll see our kappa for the constant of our dielectric, and our kappa will be directly proportional to the capacitor. So if we introduce a capacitor, it'll increase capacitance, okay? If we introduce a dielectric material between the plates, we will increase the capacitance. Yes? The E, that's, so E naught is our permittivity of free space, right? And that's 8.85 times 10 to the negative 12. That's through air. But we use not because like there's nothing there, you know, the dielectric is not there, right? But here we have the dielectric of, you know, through a specific material, okay? So actually we would use, so equals, I'm sorry, E naught equals epsilon. So this is kind of like a general formula, but this naught shouldn't be there for the true formula. We'll have E naught times our dielectric constant. Yeah.
So can you think about it like just because you introduce dielectric, that means that the space in between, since you got to get it in, your area increase, therefore.
Not quite. So this is how you should think about it. Use up all these papers. So we have a parallel plate capacitor, right? One is positively charged, one is negatively charged. Okay, we like to introduce a dielectric inside for two reasons. One, to increase the capacitance. Two, because in the real world, you know, like we have freaking 500 capacitors inside of our cell phone. They're just really, really tiny. Okay, if you had the capacitors there and you had your phone and like you dropped it, the plates would touch each other and then it would just be a wire. You know, if the two plates of the capacitor touch each other, it would just be like a normal wire, right? And it defeats the whole purpose of having a capacitor. We put that dielectric there so that, you know, even if you squish them together, they're not going to touch because the dielectric holds them between each other. But the dielectric is going to be made of you know, some substance. It's going to be insulative material, but you know, that insulative material will have molecules, okay? And those molecules, when in free space, you know, they'll just be facing, you know, in different directions. So you see it's like completely random, but then when placed in the parallel plate capacitor, they will align, okay? Each molecule will act as a, what's that called? The dipole, right? Dipole inside, and increase the magnitude of the, electric field inside, or decrease, whatever. Yeah, because of that. So they'll kind of move. They won't like flow throughout because it's a insulative material, but they'll kind of move in their respective spot.
I thought it was supposed to decrease the magnitude of the electric fields inside.
You can check up on your book and stuff. Does anyone think? Because I might be wrong. Does anyone also think that it decreases the
I mean, I don't think it's
capacitance?
I don't think it's that important.
This is super important. I definitely look it up, but I'm pretty sure it increases the capacitance. I'm pretty sure it increases the capacitance.
I mean, I meant electric field.
Oh, decreases electric field. Yeah, that's right. It decreases electric field, but if you, you know, kind of look at this equation, our potential is directly proportional to the electric field, and thus will, if we have a decrease in electric field, it increases the capacitance. So yeah. Because even if you look at it, let's actually kind of draw this out. So we put it in our parallel plate capacitor, thus all our positive charges are going to kind of go to the right in our dielectric, and thus we'll see a electric field that way when the capacitor has an electric field. I'm sorry, what's it called? We have it that way. Yeah, I definitely read about it in your book. See what they do to explain it better. But yeah, so let's take a look at a 4 microfarad capacitor. That's what I just talked. No. 4 microfarad capacitor has a potential drop of 20 volts between its plates. The electric potential energy stored in this capacitor is what? Okay, so it has 4 microfarads. So C equals 4 microfarads. We have a potential drop of 20 volts. The electric potential energy stored, okay, so big U is what? Who knows the equation for Q squared over 2C. Let's do big Q, right? Thus, for this problem, what we're going to have to do is use these two values to find Q, okay, which we can do with this up here. So we see that Q is equal to C times delta V. Okay, so then if we plug this in, we have U is equal to C squared times delta V squared over 2C. One of the C's cancel, and this will be our final equation, right? We have C times delta V squared over 2. Okay, let me just kind of like bring that closer to you guys. But yeah, y'all see that? It's a little blurry, but I'll redraw it over here. What are you saying?
Is there another equation that's like supposed to be like U equals 1/2 CV squared?
U equal, oh, that's another one we could use. So U equals 1/2, what was it?
CV squared.
CV squared.
Yeah, that's like, that's the derivation.
Yeah. So if you look at it, so let's take a look at our previous one. So we had C equals Q delta V, and then we had, what was it, U equals Q squared over 2C. We plug that in, we have, Q equals C delta V. So then it's C squared times delta V squared over 2C. The C's cancel, and then we have 1/2 delta V squared. Yeah. And it's the same thing. We just kind of derived it a little bit longer. Okay, cool. Thus, if you plug this in, we'll get, what is this number, 15D, 800 microjoules. Okay. Which one of the following is the correct unit for electric current? So what is this? A, is it volts per second? C per second, coulombs per second, joules per second, or amperes per second?
Coulomb per second.
Coulomb per second, right? Because I equals dq over dt. Q is Coulomb, time is second. Cake. Okay? So an electric device delivers a current of 3 amperes for 10 seconds. How many electrons flow through this device? This is a good one. Okay, well, kind of. Looking at our previous equation, so I equals dq over dt. We have 3 amperes equals, dq over 10 seconds. We can times it over, and we get Q equals 30 seconds, right? 30 coulombs. But we want to know how many electrons flow. So how do we convert coulombs into electrons? Yes? Awesome. So we'll divide it by the elementary charge. So if 1 electron is 1.6 times 10 to the negative 19 coulombs, we'll get our number of electrons.
I'm sorry. Going back to 15, I just had a question. Is there supposed to be is the watts supposed to be in terms of microfarads? Because if you do the calculation, you get you have the 4 times 10 to the negative 6, and then times 400 because 20 squared. And you multiply it all out, you get 800 times 10 to the negative 6.
This is UJ.
Okay. One watt?
Microjoules is joules, because we're looking at the potential energy.
It looks like a W. I was confused.
Yeah, my apologies. Small text.
Okay. It's microjoules.
Yep.
Okay.
Watts is joules per time, right? Or something like that.
Okay.
Okay, so then we get the number of electrons, and if we were to do that, okay, we'd get 1.9 times 10 to the 20th, positive 20. I don't know why there's a 3 here. Electrons, right? So there's our work.
What was the answer for that?
D, so 1.9 times 10 to the 20. A 200-watt light bulb is connected across 110 volts. Excuse me. What current will flow through this bulb? What current will flow through this bulb? So we have 200-watt light bulb. Okay, what's watts? What does that insinuate? Like power? Awesome. So power equals 200 watts, and then we have potential equals 110. What equation do we have to relate power and potential? So P equals IV, right? Awesome. So then if we solve for current, we get I is equal to P over V. We simply divide the two by each other because they're both SI units. So then we get, what number is this, 18? 1.8 amperes. Okay, any questions? No? Cool. The length of a certain wire is doubled, and at the same time its radius is increased by a factor of 4. What is the change in the resistance of this wire? Okay, so the length of a certain wire is doubled. So LF equals 2LO. And at the same time, its radius, so radius final is increased by a factor of 4. Okay, so then we have 4 RO. What is the change of the resistance of our wire? So we've determined that I'm going to use little r because, you know, resistance is big R equals rho times L over A. Okay, and if we have our wire has a radius, we can assume that it's a circular wire, okay, or cylindrical wire. We could change this to rho times L over pi r squared. Okay, so pi r squared is just the surface area of a circle, right? Cool. Thus, if we change this, okay, so we'll have this one as 1, like our initial. Then our final would be rho times 2L over pi r squared, but the 4 is going to be squared, so then we have 16 r squared, which that'll simplify to 1/8, right? So it's going to be reduced by a factor of 1/8. Okay, and that coincides with my question. Rho is resistivity. Okay, so that's like a number or value given by the material of the object. Okay, so any problems that ask you about this, they'll usually give you resistivity or ask for the resistivity. Yes. This one? Oh, this right here? Yeah, so this is rho times 2L, because I replaced the LF with 2LO, over pi times 16 r squared, because I replaced r with 4r, but I factored the square. Do you see that? And then I just simply simplified 2 over 16 to get 1 over 8. 2 capacitors of 4 microfarads and 8 microfarads are connected in parallel. What is the equivalent capacitance of the system of capacitors? Okay, so how do we add capacitors in parallel? Do we simply add them or inversely add them? Simply add them, right? So then we're just going to take 4 microfarads plus 8 microfarads to give us 12 microfarads. Okay, and then bam, cake, right? Let me just see that's not a trick or nothing. Cool, D is correct. A 4 microfarad are connected in series across an 8-volt DC source. What is the charge on the 6 microfarad capacitor? Cool, so now we got it. I see a problem like this, I'm gonna draw it out, right? So we have a capacitor. So here's C1, here's C2. They're connected in, series. C1, C2, and we have an 8 voltage source. Okay, so here's Inf equals 8 volts. What is the charge on the 6 microfarad capacitor? So what we like to do for these kind, this is a very simple version. What we'll do is we'll just get a equivalent capacitance. Okay, so C equivalence. We know this is still 8 volts. Okay, so our C equivalent will be 1 over C1 plus 1 over C2 inversed, right? And then we're looking for the charge on the 6 volt capacitor, and the 6 volt capacitor, let's call it C2. Okay, so we find the charge by looking at our previous equation, right? We have C equals Q over V. Okay, so that means the charge on our equivalence capacitance is just Q equals 8 volts times our C equivalent, which is essentially this pajazz over here. And then we separate the two, okay? So when we separate the two, will our potential be the same on both, or will our charge be the same on both?
The charge will be the same.
The charge will be the same on both, okay? So when we go from, when we break up our capacitor or our resistor in series, the charge will be the same on each. Okay, but if we break them up in parallel, our potential will be the same on each. Okay, how I like to remember that is the potential will not be the same, because after each one, the potential drops some value. But when the charge goes through, the charge that builds up here will, attract a similar charge on the other one. Okay? And just like resistors, if we had resistors there instead, the same thing will happen. Across each of them, we'll have some potential drop. But if they're in series, the current will be the same if we go through two. But if we break it up in parallel, the current will be different in each of them. Okay? So let's see. Yeah, so since the charge is the same on both, we don't even need to do anything else. Right? We found the charge for the equivalent one, we break it up, but that charge stays the same on each. Okay, if it asks for the potential on both, we'd have to do a little bit more work. But if we were to work this out, we'd see that our answer would be C, 19 microcoulombs. We just plug C equivalent in for that. We have 8 volts times 1 over C1, which is 4 microfarads, so 4 times 10 to the negative 6, plus 1 over 6 times 10 to the negative 6 inversed. Okay, or 8 divided by that, if you'd rather look at it this way. Okay? Any questions? On my, what's it called? It's Monday session, I'm going to have a really big one of these. Really big one of these. A 5 microfarad capacitor is connected in series with a 3 kilo ohm resistor across a 20 volt DC source and an open switch. If the switch is closed at t equals 0 seconds, what is the charge on the capacitor at t equals 9 milliseconds? Okay, so again, I see something like this. I'm gonna draw it. Luckily, they supplied me with hella paper. Okay. So we have a 5 microfarad capacitor connected in series with a 3 kilo ohm resistor across a 20 volt DC source. So here we have our 20 volt DC source, a resistor, and then a capacitor. So we have 5 microfarads, and then we have, so we'll just call this C equals R equals 3 kilo ohms. Okay. The switch is closed at t equals 0 seconds. What is the charge at the capacitor at t equals 9 milliseconds? Okay, so what equation are we going to use for this? Who can read this question and think what equation we're going to use? The exponential one, right? So we'll have something like the current is equal, so the current at any point is equal to like our max current times, what is it? Is it 1 minus e or e to the, or simply e to the what? RC, where RC is our tau, okay? So tau equals RC. Okay, and that's like our time constant. So looking at this equation, okay, we'll see our R max is given by what?
Exponent is negative t over RC, right?
Yes, sir.
The IMAX?
Imax, what is, how do we find that? 5.
Oh, no, sorry.
You don't know? Anybody?
Is it just or V over R?
Awesome. So V over R. So we can essentially simplify this to V over R times 1 minus e to the negative tau. So e to the negative t over tau, which is just our RC. We can solve our RC by taking the resistor times the capacitor and plug that in. But let's do this math for real, because I want to determine if it's 1 minus E or simply E, because over time we're adding charge to the capacitor, right? Does that make sense? I'm sorry. Yeah, so we're adding charge onto the capacitor. And this is just giving us our current. So how are we going to find, like, what are we going to do to find our current onto the, how are we going to compare our current to the charge on the capacitor? dq by dt. Awesome. So we'll have dq by dt equals our current. Okay, so once we get that, we'll be able to take dq by dt. But what I was saying by like determining if it's 1 minus e to the negative 2 over tau or simply e to the negative t over tau, because as time goes on, we're accumulating charge on the capacitor, not losing charge, right? Does that make sense? Question?
I was going to say, like the t is increasing, so like as t goes to infinity, you're approaching e to negative infinity, which is
Oh, okay.
0.
Awesome.
So you're getting closer and closer to 1.
So you're getting closer and closer to 1. So as time goes on, this value will increase, the total value. Does that make sense? Because if we increase t, e gets smaller. And 1 minus, you know, if e was large, right, then we'd have a small number. But if e was small, then we'd have a big number. Does everyone see that? Awesome, thank you. So then dq over dt, but if we're looking just like kind of, you know, like if it's not, you know, increasing in a linear, like a curved fashion, if it's increasing at a linear fashion compared with each other, we can use delta q over delta t. So then the charge, essentially, q will be t times v over r times 1 minus e to the negative t over rc. Okay, and if we plug this in, we get C, 45% of its maximum. Okay, so how this would give us like a specific value. This would give us a specific value, but if we were to, what's it called? What would we do to get a percentage? So our original, actually, we didn't even need to do any of this stuff, okay? A percentage we could essentially get by having I at that given point, you know, like, so I sub t, right, over I max times 100, which will equal, we just kind of divide over the I max to give us that ratio. We times it by 100 to make it a percent, right, because this will be smaller than that one. So it'll give us some decimal. We multiply it by 100, and then essentially we'll just have 1 minus e to the negative t over RC. Okay, but this will be times 100. You know, if I do something to one side, I have to do it to the other side. Cool, so that's why you read the answer choices first, so you don't have to do extra work. Any questions on that?
Isn't there another equation just for Q that we could use?
So if we look, you know, we break up both of these, like I is dq at a certain time. So it's q at a certain time, and then over q at a max time, so like say final or whatever. But this is dt over dt, like the change in time will cancel, and then it's essentially the same thing. You know, you can break these up over here and then cancel the times, but that's how you'd get your charge. So if you had in your formula sheet, you know, that equation for charge right away, you can just start off with that one. But if you're just given, you know, the current equation, then you'd have to derive it. Okay. Yeah. Cool. Any questions? Good question. Thank you.
Does that say at the top right corner tau is equal to RC?
Yes, sir. Anything else?
We got you some.
Oh, cool. You're the bomb. You're the bomb. Okay. Let's see. What time is it? 9. Okay. A proton moving with a velocity of 4 times 10 to the 4 meters per second enters a magnetic field of 0.2 Tesla. If the proton travels in the direction of the magnetic field, what is the magnitude of the magnetic force on the proton? Skip 23? Oh, wow, I didn't even see that one. Okay, so a proton is projected with a velocity of 7 times 10 to the 3 meters per second, thank you, into a magnetic field of 0.6 Tesla, perpendicular to the motion of the proton. What is the force that acts on the proton? Okay, so who can tell me what our equation for magnetic force is? Awesome, thank you, Jermaine. So QV being our velocity cross B, okay? QV cross B. Since they're perpendicular, this will equal to Q times the magnitude of V times the magnitude of B, right? Because it's sine of the distance between the two, the angle between the two, and we know that the angle between the two is 90, and sine of 90 is essentially 1, okay? Thus, you know, we plug in our numbers. We have the charge of a proton, which is 1.6 times 10 to the negative 19. Okay, the velocity is 7 times 10 to the 30, and then times the magnetic field's 0.6 Tesla. And these are all SI units, right? Thus, we can simply multiply them out together. With that, we get 6.7 times 10 to the negative 16 newtons. Okay. A proton moving with a velocity of 4 times 10 to the 4 meters per second and a magnetic field of 0.2 Tesla. If the proton travels in the direction of the magnetic field, what is the magnitude of the magnetic force on the proton? Awesome, 0. Okay, so here we'd have our equation, but it would be sine of 0, and sine of 0 is just equal to 0. Anything times 0 is 0. Okay? So watch out for problem like that, right? An electron moving perpendicular to a magnetic field of 4.2 times 10 to the negative 2 moves in a circle of radius 0.4 centimeters. How fast is the electron moving? Cool, this is a good. So it's moving perpendicular to the magnetic field. Okay, it moves in a circle of radius 0.4 centimeters. So let's take a look at this. 0.4 centimeters. We have, it's moving, its velocity is perpendicular to the magnetic field. So let's just say it's moving into the page. How fast is the electron moving? So let's find this velocity. What equation do we know? Anybody? Like, what's going on here? Why is it going in circular motion? Centripetal force, right? Our magnetic force in this situation is going to equal our centripetal force, because our centripetal force is any force that keeps a particle or object in circular motion. Okay, so like if I'm swinging like a rope or something and with a ball at the end in a circle, the centripetal force is the tension. If I'm driving a car around a curve, the centripetal force is the friction on the ground. Okay, etc. If we have a particle moving across the magnetic field, so let's take a look at this. It's going that way. We use our right-hand rule because we have a cross product. So looking at the cross product, we'll take the first variable, which is our v, in the direction of our thumb. Okay, so if we look at this bottom point, our v goes to the right, our magnetic field goes in. Thus, our force will go upwards and the direction will change. Okay, so the direction will change upwards, but then as the direction continuously changes, the force will constantly be pointing towards the center. Okay, so we know that our centripetal force is equal to our magnetic force. Who remembers what the equation for centripetal force is?
mv squared over r.
mv squared over r, awesome. So mv squared over r, if we set these two equal to each other, so we have q, I forgot the v. So q, v, and they're perpendicular, so we'll just do the sine 90 type stuff, equals mv squared over r. Okay, we're looking for velocity. One of those velocities cancel out, so we divide both sides by r, and then we divide by m as well. So then we get velocity is equal to q times b over m times r. Okay, r being the radius. Okay, yeah, cool. We have charge, q is equal to, this is a, what is this, an electron? So 1.6 times 10 to the negative 19 coulombs. Then we have magnetic field is 4.2 times 10 to the negative 2 Tesla. And then we have radius is equal to 0.4 centimeters, but that's 0.004 meters, right? Going to SI units. What about mass? What's the mass of an electron? Yeah, so 9.11 times 10 to the negative 31 kilograms. Oh, yeah, my B. Okay, so here are, right, because we bring it up. Good catch, thank you. Good catch, thank you. Man, I'm crazy to see how my next session goes. Got one right after this.
Oh, for anatomy?
But yeah, any questions? No? Cool. I apologize, like I'm standing right in front of the screen and all of you guys are like, but it's just the way it is. Okay. If we solve this out, we'll see number 25 is equal to 3 times 10 to the 7th meters per second, right? Who calculated that out? Nobody. Yeah, it worked? Cool. Awesome. A loose spiral spring carrying no current is hung from a ceiling. When a switch is thrown so that a current exists in the spring, how does the coil move? Okay, so let's take a look at this. We have a loose spiral spring hanging from the ceiling. When a switch is thrown so that current exists in the spring, how does the coil move? Okay, so current will go into the spring, I assume. So this is a poor question because it doesn't tell which way current will go. But let's just say current goes in, okay? And if it's different from my answer choice, then like it's just a, what's it called? Poor question making on my part. But yes, so we'll have current going this like such. You know, if we want to add all our vectors, not vectors, but arrows, okay? Because current is a scalar quantity, right? We'll see using our right-hand rule that current's going that way, thus in the center of the coil will have magnetic field going up or down? Up. Awesome. So magnetic field inside will be up. Okay, magnetic field outside will be the opposite direction, right? Okay, so if the magnetic field is up, will the coil like get close to each other or closer? Why? Pushing it up. Awesome. But actually the key concept we want to look here, that's a good way to look at it, but we want to see that we have an increasing current actually. Okay, so it doesn't really matter whether the current is going up or down. Now that I think about this further, it can go that way or the other, but if we have an increasing magnetic field, okay, that means our induced magnetic field will be in the opposite direction, right? And essentially what they're going to want to do is like attract each other. Each of the lines will come together, okay, and our coil will come closer together. Does everyone see that? Kind of? Wants me to explain it? Yes?
Even if the current went through the opposite way, it's still contact?
It would still, so even if current would go the other way, because it's not about the direction, but it's about the direction of the induced oomph compared to the other one. So we have an increasing current, okay, and that induced oomph will create a magnetic field opposite to it, and thus the magnetic field caused by like the other one will be opposite to the magnetic field at the top of the wire, you know, because it takes time for them to get to each other, and they'll attract each other. Okay? So, you know, save this problem, kind of draw it out, definitely ponder on it a little bit more. It's a pretty interesting problem, actually. But, yeah. Any questions?
Just to make sure, if you have a decreasing magnetic field, then that means that the induced current is in the same direction.
The decreasing magnetic field will cause a induced magnetic field in the same direction. Awesome, thank you. And that's Lenz's law and Faraday's law at play there. Okay? So definitely know Lenz's law and Faraday's law. I'm just going to put like a star there.
Wait, but what about that induced magnetic field causes them to like come closer together?
Because so like the part of, so since this one's changing like faster than the bottom, we'll have a magnetic field that's kind of going up. And then the other one will have a magnetic field that's going down. And that's kind of like a north pole and a south pole. And then a north and a south pole will want to come together.
But but can't you think of the current as like instantaneous, like, you
Yes. So current is instantaneous. You're right. That is a very good point. To elaborate the logic, we'll see, our induced oomph being kind of delayed because it's not like a perfect wire. You know how we'll have a change. So here's our B induced. And essentially, like, all you really have to look at is in between two of them. We have one magnetic field going down, but then it induces a magnetic field going up and then down. Instead of like,
Isn't it that induced current, it's just like for a little bit, eventually?
yeah, eventually.
About that instinct, so.
Yeah, eventually the induced current will die out. You know, if you have an inductor, if you guys remember, like as soon as you close the switch, the inductor will act as an open, like a cut in the wire, because it just returns the currents back at an equal magnitude, canceling the currents. But then over time, like nothing's perfect, so then the currents will continue and flow through it because it's not changing anymore. And it'll act like a straight wire. Because for inductors to work, there has to be that change in flux. But yeah, so we'll have a change in flux here, and then that change in flux will be in the induced flux will be in the opposite direction than the original one created. And so just kind of think of those two, the induced flux from some loops, from the loop below it, or even the loop above it, will be opposite to its original one, and then it'll kind of like coil together. Okay, come closer together. And there's actually a YouTube video explaining this problem. Would you guys like me to look it up now, or? Yeah? Okay, let's do it. Hold on. I apologize. The internet's not working right now. But just look up. Let me get back to you. How did that happen? Go to RGB. Okay. Okay, so hanging coil electromagnetism problem. Okay. Any other questions before we continue on? Cool. So here we have a wire carrying a 2 ampere current is placed at an angle of 60 degrees with respect to a magnetic field of strength of 2.2 Tesla. If the length of the wire is 0.6 meters, what is the magnitude of the magnetic force acting on the wire? Okay. So we have a current carrying wire within a magnetic field. So here's magnetic field, and we have a current carrying wire with 60 degrees, theta equals 60 degrees. If the length is 0.2 Tesla, no, if the strength is 0.2 Tesla, and the length of the wire is 0.6 meters, what is the magnitude of the magnetic force acting on the wire? How are we going to do this one? Awesome. So we'll have we have a new one, kind of ish. It'll be IL cross B. Okay. And essentially, we have the cross product, but we find an equation for the magnitudes as such times sine of 60 degrees, and we just plug it in from here. So we have our current, we have our length, which is 0.6 meters, we have our magnetic field, and we have our sine of 60. And if you forget, like, if it's sine or cosine, like sometimes all these, I always do that too. What I like to think of is we want the magnitude that is perpendicular to our magnetic field, right? So what we're going to do is we're going to break up our current. So here's our current. We're going to break it up into its perpendicular and its horizontal components. So here's theta. We'll have two components. We'll have this, which is I sine of 60, and then here, which is I cosine of 60. Since this one is parallel with our magnetic field, we know that magnitude is going to multiply by it and be 0. And thus, this total will be what's left, okay? So that's kind of like a nice little trick, just when in doubt, draw some triangles, okay? That's my motto of physics, okay? And if we plug this in, we get, let's see, C? Come on, bro, what number is this, 27? D. Yeah, it's close. We haven't had a D in a while either, right? D, A, B, C, and then D. Here's our D. Yeah, it was do fit, okay? And when in ultra doubt,
Just pick what graph.
yeah, start using your statistics, right? We all ace statistics. Right? We all ace statistics. Oh yeah, the exam is even multiple. Sorry, my bad, bro. This doesn't even apply to you guys. The exam isn't even multiple choice. But yeah, moving on. A rectangular loop of wire carrying a 4 ampere current with certain dimensions is placed in a magnetic field of 0.6 Tesla. The magnitude of the torque acting on the wire when it makes a 60-degree angle with the field is 1.1 Newton meters. What is the what is the area of this wire? What is the area of this wire? Okay, this is a pretty interesting question. We could derive our way to it, breaking it down. Or we can, see in our formula sheet the torque equation. Okay. What do you guys want to do? Raise your hand if you just want to get the equation, or raise your hand if you want to look up do the entire derivations. So raise your hand for derivation. Raise your hand for just pull out the equation. It's fairly even, but it seems like more hands for derivation. Okay, so let's go through it real quick. It'll be more helpful. So we have a, like wire acting as a dipole in a magnetic field. Okay, so let's imagine the magnetic field is going into the page. Okay, and I made the coil look like this because this top part is a little farther back than this front part. Because if it was, it was perpendicular completely to the magnetic field, then it wouldn't act. It would be like a dipole in equilibrium, like stuck there. We're looking at that point of the dipole where it's feeling torque. Okay, so this angle is important. So if we were to look at this from the side, okay, so here's kind of like our axes here. This is just some axes that I made. We'll see this, okay, and if the current is going clockwise, and if I rotated this from here to the side so that our left-hand wire is closest to us here, our current is going upwards, right? Okay, and then the current at the top of the page is going in, and the current at the bottom is coming out. See if I can do this. We know that the force on the wire is given by F equals IL cross B, and this is simply derived from our other one, Q V cross B. We break up V into into length, the length it travels over time, and then Q, charge over time, is simply current. Okay, does everyone see that derivation right here between these two steps? So we have this is essentially like the length over time, and then Q over T is our current. We just kind of move the T over. But yeah, so we have force equals IL cross B. Looking at the top one, our force is going to be in what direction? So if our magnetic field is going to the left, right, here, we have our magnetic field going to the left, our velocity is going in, so we'll see a force coming out upwards. Okay? So we see a force coming up, and that force is going to be given by this, except it's the cross product, right? Well, here we see it's actually perpendicular completely because the current's going in and then the magnetic field's going that way. So the magnetic field and the current are actually perpendicular to each other. So this will be its complete magnitude. Okay, does everyone see that? So we have the complete magnitude here. But if we're looking at torque, okay, what's our equation for torque? What'd you say? B dot A? Does everyone agree? Well, what's our physics 1 equation for torque? What's our physics 1 equation for torque? What do you guys?
Perpendicular force times your distance.
Awesome. So perpendicular force times our lever arm. And essentially lever arm sometimes like encompasses the definition of perpendicular. Okay, like if I had a string on that door and like I pulled the door open, like the torque only applied would be the component that's perpendicular to the lever arm, which is the frame of, like the face of the door. Okay. So yeah, we want the perpendicular force to the lever arm. So let's say that this is the lever arm, right? From the point, like from here to here. So lever arm. We see that force. We want the perpendicular force here. Okay, our perpendicular force would thus, if we broke this up into two components, some theta here. So force perpendicular would equal our original force times cosine of theta. Okay, and let's try and get this theta with respect to our, what's it called? Yeah, our normal vectors and stuff like that. So if we see our normal vector to the plane as such, so here's our normal vector n hat. Okay, and let me just zoom in a little bit for you guys, because there's a lot going on here. So here's the normal vector. Okay, we have our magnetic field going here, and then our theta going there. If you notice, like, as we increase the normal vector, our force always stays up. But as we increase the normal vector, the angle between here will be increased. So here's our force perpendicular will always be to the right, okay? But as we curl our normal vector, our force perpendicular will curl just as it does, okay? And if we know the force going up is 90, right? So let's just kind of make a little triangle here. And we know it's perpendicular to our magnetic field. We can call this some angle phi, which is essentially equal to 90 minus theta. Thus our force perpendicular, okay, is going to equal F sine of phi, where phi is the angle between our normal vector to the plane and the magnetic field. Do you guys see this? Everyone following me? Raise your hand if you need me to explain something. No? Cool. So we have this as our torque. So thus our torque is equal to the force, which is I L cross B, okay, times the lever arm, okay, and these are just magnitudes, so I'm going to kind of forget about that. And don't think of that as a dot product, just think of it as a multiplication of the magnitudes, okay? It gets confusing with all these different types of multiplications, don't it? But if we notice here, length, this will be the torque. I'm sorry, let's just go back real quick. This will be the torque for half, but the same thing is happening in the bottom, but in the opposite direction, right? So we can multiply this equation by 2. Does everyone see that? Okay, so this length right here, I'm just going to make a parentheses, 2L times capital L, okay, so 2 times our lever arm, which is this, and L is the length of, you know, the wire. We have a square wire here. Is simply equal to our area. You guys see that? Thus, we could simplify 2L times L, 2 little l times big L, into IAB, and I forgot our sign of phi, right? IAB sine of phi. And then like we can introduce what's called our like magnetic moment, right? Magnetic dipole moment. Okay, and we define magnetic dipole moment as IB, right? NIA. Oh yeah, NIA. So NIA. What's this N here? Why do we have magnetic dipole moments as NIA? Number of turns. So this is just for one loop. But if I were to come here and wrap this into a coil, each one of those wires would feel a force. Thus for every turn, okay, it will be multiplied bigger, okay? So if we have 2 turns, then the torque would be double. If we had 3 turns, it'd be tripled, quadrupled, etc., etc. Does that make sense? Thus, we have our torque equal to mu naught B sine of phi, where phi is the angle between the normal to the plane and the magnetic field. And that's just like a fun little derivation, okay? But yeah, where magnetic dipole is number of turns times I times A. Okay, and then if we were to plug in our variables, right? So we have a rectangular loop of wire carrying a 4 ampere current. Okay, so this is going to equal a N, let's see what N is. We'll put that last if we have to, but I is 4 ampere, excuse me, so 4 amperes times magnetic field, which is 0.6 Tesla. Acting on when it makes so we'll have sine of 60. The magnitude of the torque acting on it when it makes an angle of 60 degrees with the field is 1.1 Newton meters. What is the area? Oh, so we're given torque. So this is 1.1 Newton meters. But we're going to solve for area by dividing them all out. Thus, area is equal to 1.1 Newton. 1.1 Newton per meters over 4 times 0.6 sine of 60. Okay, and if that's the case, we'll see we get 0.53 meters squared. Okay, is that what you guys got when you did the calculations yourselves, like all of you most studiously do? Cool. Thank you, Hunter. Question.
So I know that for some problems we use like the other angle. So like in this case it would be like sine of 30. So can you explain again why it is sine of 60?
So actually here it's a little ambiguous, okay, because it says when it makes 60 degrees, the magnitude of the torque acting on this wire when it makes 60-degree angle with the field. Okay, we're physics 2 with calculus. When we talk about the angle between the planes, it'll be between the normal vector to the plane and the magnetic field. But sometimes the question might specifically state it has an angle between the plane of the coil and the magnetic field vector. Thus, if that's the case, it'll change our calculation such that we take our, what's it called? We take our angle to be that here. So we'll take this angle right here, okay? And if you look here, that angle is simply phi, okay? But we, instead of switching our theta, from 90 minus theta to sine of phi, we'll just use cosine we'll use cosine of that one, okay? Or you just, you can just look at your triangles and be like, okay, do I want to do 90 minus the angle that they give me? Or do I want to do like cosine instead of sine of the angle that they gave me? But essentially, you'll use theta, sine theta. So you'll use sine theta when angle is when angle is between plane and magnetic field vector B. Use sine of phi when angle is between normal to plane and B. Okay, that's a very good question. Thank you, Pauline.
So you use sine of both, right?
Yeah, sine, but it's different angles. Okay, so here's phi and here's theta. Okay, and if we look here, here's phi, but here's theta. Okay, I'm actually gonna pause here, and there's still, more to the review. You have it online. Okay, you can do it yourselves. I'll post up the answer key to my WordPress site so you guys have those and you could compare your answers. I'll probably do that tonight or tomorrow morning, okay? But questions. This is now like we have 6 minutes for any questions you guys have. Yes?
Your WordPress site?
My WordPress site is ucfsi.wordpress.com. Okay, so you're going to get the original review. Sorry, I'm making this like super complicated, but you're going to get the original review at UCF Study Union.wordpress.com. Okay, so the original review is at ucfstudyunion.wordpress.com, and the answer key will be at ucfsi.wordpress.com. Question?
Is there any chance that like are you doing a worksheet on Monday or how? Like,
Yeah, so I will have a different worksheet on Monday. It's not going to be multiple choice. On Monday, it'll be like a question, and we're going to work out through
is there
it.
any chance you could like post that sooner? Because my test is on Monday, like before your session.
I'm going to try to get it by tomorrow, noonish.
Okay, just as long. Okay.
Yeah, I'm going to try. I still got to make it. Not even going to lie. Like you'll see.